Okay, I'm going to do the last two sections, 1412 and 1413, as one unit, the quality of sound and the ear. Let's start off with the quality of sound. This is 1412. Now you have, when you strike a tuning fork properly, you'll only get a single frequency. You'll only get the tines of the tuning fork um, operating at the fundamental. Now, uh, when we do tomorrow, when we do the experiment, if you were to strike the tuning fork on a hard surface, you will generate overtones. In other words, not only will you get the fundamental, but you'll get these weird uh, other shapes where um, you know, you'll have nodes and antinodes on top of the fundamental in vibration. So if the tuning fork is hit properly, yes, there's only the fundamental, and you can see that the flute has different harmonics that make up its sound. A clarinet, a different set of harmonics. In case you're interested, uh, this goes into Fourier analysis. Any repeating signal can be broken up into its components. Uh, all the different harmonics at different intensity levels, and that's where we get the quality of sound. That's how you can differentiate between a flute and a clarinet and a guitar string, a saxophone, the different instruments. Um, so there's different qualities that we have, or it's called the different qualities of of sound, and it comes from all the different harmonics that are generated out of the musical instruments. Now, the ear is an amazing piece of engineering. It's got uh, the ear canal, the inner ear, made up of the hammer, anvil, and stirrup, and the cochlea. These all have to do with hearing. Um, the but there's so much more to the ear here. So sound waves come in using the superposition principle. Remember, I told you that there's not going to be a sound for a sax. If you're listening to a band, there's not a set of air molecules that are the saxophone and the set of air molecules that are the guitar. They're all kind of superimposed over one another in what is called the superposition principle, so that you're getting one wave front with all these different wave shapes hitting you, and that hits your ear. The ear hits the hammer, which vibrates the anvil, which vibrates the stirrup, and uh, causes the vibrations to go down the cochlea, and the cochlea resonates with the different sounds that it hears, and it turns it into to hearing. But there's a whole lot more at the ear. That you have the semicircular canals for balance. Basically, what they are is it's an orthogonal, three orthogonal gyroscopes that sense motion. Not only that, you have what are called otoliths, which are little tiny, basically rocks. You have rocks in your head. You really do. The otoliths are little rocks on little fibers that they're accelerometers. So that if you're still, let's say you're still in a car and you accelerate, the little otoliths, they suddenly go back and you get the sensation that you're moving. And if you come to a pause, once you're going into steady state, those otoliths come back, and once you stop, the otoliths will sense that you're stopping. So there's really a whole lot more than just hearing going on in your ear. The Do they show the? No, that's it. They don't show the. Oh, yes, they do. Yes, they do. Uh, these are the um, the threshold of hearing, the 0 dB. Notice that it's not flat. The response is dependent on the frequency. The widest range is around 350. That's where 3,500. I said 350. 3,500. That's where we have our widest range. In other words, a sound that's really high has to be higher than, let's say, 3,500 in order to be heard. And this is the frequency response for different sounds at different intensities. And that's about, you can study that in detail if you need it for your, it's section 14.13, the ear. I probably haven't covered it in the detail that they cover it here, but I'm not going to test you on it. So if you're interested, go ahead and read it and study it if they have questions on the MCAT. So that's it. That ends our section 14, or topic 14, chapter 14 discussion.